Okay. So my aim in this lecture will be again to select a few topics which you could call astrophysics, but I prefer to call it simple models and some numerical estimates. So again, I'll try and cover concepts which apply across a range of astronomical objects. The same theoretical ideas sometimes can work across a range. And like the previous time, I may not be able to go into great depth, but I'd be happy either during the talk or later to elaborate. Okay. So, one way of looking at astronomical objects, they usually tend to be objects in which gravity is important. So, I've straight away written down Newton's constant, right? And I'm kind of asking the following question: is it large or is it small? It looks small, 10 minus 8, right? But obviously, it's not. It's a dimensional quantity. So the numerical value is going to depend on what system of units you use. So just to make this point, I have converted it to a different set of units. So I'm using the mass of the sun instead of the gram. I'm using the astronomical unit, the Earth-Sun distance, instead of the centimeter. And instead of the second, I'm using a period of 2 months. And then I'm sort of guaranteeing you that G is going to be 1 in these units. And I can promise you I didn't actually do this calculation. I didn't really substitute the known values of the mass of the sun to get this 1. But my confidence comes from a simple calculation which we can make. I will. If you take the Earth going around the sun, right? And in a period of 2 months, it roughly travels by the 60 degrees or 1 radian or something like that, right? Okay. And this is the mass of the sun. Right? And you have this equation, which I'm sure some form of this equation you must have seen. Well, okay, if you want the centrifugal force, you can equate to this. Right? Now, I have chosen the units in such a way that m is 1 because the mass of the sun is a unit, r is 1 because it's the astronomical unit, and then omega is 1 because the period is 1 year, but omega is 2 pi divided by, so omega, inverse of omega is the time taken to travel 1 radian. So therefore, G is guaranteed to be 1, okay. So this is just to make the point that if you use the appropriate units, appropriate to whatever system you're interested in, star, galaxy or something, you will find that G is quite important, okay. So, I mean, no need to rub this in. So if you say something small or large, please be careful and make sure that it's dimensionless, okay. And if it is dimensional, compare it with something else which has the same dimensions. So I gave you a definition of astrophysics as studying the whole universe. I'm giving you a different definition now. The physics of systems in which G is 1 or G is important when expressed in terms of the scales appropriate to the system, okay. Now, a lot of the things I'm going to tell you are going to be very approximate, very rough. Of course, astrophysics used to have the reputation of being a very rough subject because the observations were not very accurate, the theories, so people would do a lot of order magnitude calculations. Still worth doing it as a first step, but it's no longer true. In almost every branch of astrophysics, a lot of precision has been achieved in the modeling, both because of improved observations, improved theories and improved computation, okay. So therefore, I'm not suggesting that whatever I'm going to do in the next hour or so is all that there is to astrophysics, but for a first view, that's okay. However, I thought it's nice to begin with at least one statement where I can write an equal to sign, which is right. So that's why I have chosen this. I don't know how many of you have come across this phrase called virial theorem. So it basically concerns some set of particles, and they are labeled by I. Mi are the masses, Ri are the vectorial positions, and if you take Ri dot Ri, it's just the distance squared from some origin. Okay, and if you weight it by the mass, I'm calling that I. I is kind of like a moment of inertia, right? Which many of you may have encountered. Not exactly, because it's the distance from the origin, not distance from some axis, right? So you can ask, why did you define this? And the answer is, Clausius found that it's a good thing to define. Then I have also defined the kinetic energy by the well-known formula, half mv squared. And the potential energy is product of the masses and inversely proportional to the absolute value of the distance. So that's a scalar. And you're saying I less than j to make sure you don't count it twice, right? That's all. So then what the theorem says, and I'm not deriving it, but it's not difficult to derive, that if you take the second derivative of I, okay, it's exactly equal to twice the kinetic energy plus the potential energy. Okay? In fact, you can get a quick idea of why. To take the second derivative of this, you have to look at two kinds of terms. Those in which you differentiate this twice and don't differentiate this at all, or when you differentiate each of these once. If you differentiate each of these once, of course, you will get the kinetic energy, but it will come with a factor of 2, right? If you differentiate one of them twice, you will get the force. But the gravitational force, again with a dot of r, will become like the gravitational potential. So that's basically the derivation of this virial theorem. So what does it really tell you? And we're really going to apply it to, I mean, it's useful. You can, as a theorem, it's fine. You can apply it to anything. But many of the applications deal with situation where you can say that the left-hand side is either 0 or small. And see, at any given moment of time, it might not be. Okay? Particles are moving around. So we are not talking of something which is in static equilibrium. It could be a star cluster, so everything is moving around, or a galaxy. However, one can average it over a certain amount of time. And then you can ask, is the system expanding overall, in which case left-hand side might be positive, or is it collapsing, in which case the left-hand side might be negative. But if the system has settled down to some kind of bound state, and star cluster is probably a good example, then you could think of the left-hand side as being 0 on the average. So average over some time, and you say the left-hand side is 0. So what does this tell you? First of all, remember V is actually a negative quantity. Okay. Yeah, I have a minus sign in front of it. Okay. So what this basically tells you is that the kinetic energy is minus half the potential energy, right? And the potential energy is itself negative. It better be, because the kinetic energy is definitely positive. But the interesting thing is it says it's half. By the way, you notice that we use the inverse square law here, right? Because we really had r dot the force, and that became the potential because the force was 1 over r squared, so it became the potential. So it applies equally to any other situation where you have the inverse square force operating. So in particular, it applies to the hydrogen atom. So many of you know that the binding energy of the hydrogen atom is 13.6 electron volts, which is made up of a minus 27.2 potential energy and a plus 13.6 kinetic energy. And even when you study the Bohr atom, you can readily calculate, and these two will be true. Of course, you might worry that the hydrogen atom is governed by quantum mechanics. But remarkably, this theorem is true in quantum mechanics, though the proof is very different. If you are dealing with a quantum system in a bound state, perfectly true. And in fact, it's a very useful guide, because it's very hard to find an exact solution either for a star cluster or for a many electron atom. It's a guidance. Okay. Yeah. So I've already, it does assume non-relativistic motion, because I said the kinetic energy is half mv squared. But apart from that, As I said, that's why I said it's a nearly exact statement. I wouldn't call it a solution of the equations of motion. Newton's laws have second derivatives, and this also still has second derivatives. So it's just a clever combination of the different Newton's laws in a form which is useful. By the way, Clausius, you might remember, is the man who gave you the second law of thermodynamics, and he applied it rather cleverly to an ideal gas, which I can tell you about later, not in this lecture. But it has a very interesting consequence. So I'm here talking of a system which obeys the virial theorem. It has some negative potential energy, and half of that is the kinetic energy. And this is the total energy, which is still negative, right? Which is why it's a bound system. Now suppose the system loses energy. This is not completely hypothetical. At the turn of the 19th to 20th century transition, people were worrying about the sun's source of energy. And at that time, what they could think of was that the sun it's definitely losing energy, right? I mean, because we receive it. The sun is contracting. And the potential energy term has a 1 over r in it with a negative sign. So if it's contracting, the energy is becoming more negative. Except it also tells you that the kinetic energy is becoming more positive. So that's what these three pictures are supposed to show you. So you have a star which is not burning nuclear fuel. At that time, of course, people thought it was the sun. But very soon they were proved wrong, and I'll tell you why. But it certainly applies to the early stages of the formation of a star. So let us say a star is formed, and these are called protostars, and people do detect protostars. They are losing energy and presumably contracting. Okay, so their source of energy is really gravitational energy in that sense. So in fact, we'll come to how much this energy is and so on right at the end. I mean, just that's the way my lecture preparation went. So this is sometimes called negative specific heat. And it's curious because this object is losing energy, so you would expect its temperature to go down. But actually its temperature is going up. So as this protostar contracts, it actually gets hotter and hotter. Of course, the temperature is not uniform inside because you need a temperature gradient for the energy to come out. And finally, the temperature in the center becomes enough to start some nuclear reaction, and then the source of energy is something else. So even that is not inexhaustible. Okay, so that's the virial theorem, but can also be it's a standard way of estimating the mass of some system. You have a cluster of galaxies, so you can measure their velocities. Of course, there may be some overall common velocity because of the expansion of the universe, but then you measure the variation around that mean. Of course, you're only measuring the radial component. In that case, you will not be able to measure the transverse components. But you say, okay, be a sport, this is probably spherically symmetric, and therefore the remaining two components you can make up by putting a factor of 3. So you still don't know the kinetic energy because you don't know the mass of the individual galaxies. However, you know the kinetic energy term is proportional to m. Then you put the potential energy term. Now, of course, to know r, you have to know the distance and the angle, which let's say you have done. But the nice thing is that is proportional to m squared. So when you have kinetic energy is half the potential energy, one is proportional to m, other is proportional to m squared, you can find the mass. Now, the strange thing is that this calculation was actually done by a Caltech astronomer called Zwicky in 1930s. And he came up with a mass for those galaxies in the cluster, which was much more than what people thought. See, people knew the amount of light coming from those galaxies. And if you assume they are all stars like the sun, you would have something called mass to light ratio. If you express mass in terms of the mass of the sun, express light in terms of light of the sun, then m by l is 1 for the sun. But suppose m by n turned out to be 10 for either these are some totally different kind of stars, which is unlikely. I mean, so he pointed this out, and then people forgot about it for, I don't know, maybe 40 years. I mean, maybe there were more pressing problems in astronomy, but it came back. And today, you will keep hearing the word dark matter. We do believe that these clusters of galaxies and even the individual galaxies have quite a bit of dark matter in them. But think of it right now as an application of the virial theorem. Okay, so let's say you have some object whose mass is given to you and whose size is given to you, and that's it. And you're also given the value of Newton's constant. What can you do with it? Well, even without Newton's constant, you can calculate the density. Okay. So every one of these equations you can just verify from dimensional considerations. Okay. If you take gm over r, it will be the square of some velocity. Now, what velocity depends on a more precise calculation. So, for example, for the Earth, if you take something which is orbiting, low Earth orbiting satellite, just above the surface of the Earth, that velocity will come out to be 7 kilometers per second. Just gm over r, as it turns out. That same equation which we saw over there, if you convert it to velocity. But if you want it to escape, then it will be 11, which is square root of 2 times that. So, the exact numerical factor in such equations depends on the context. But the dimensional analysis tells you that velocities associated with this system in which gravity has some role are going to be of the order of gm over r. Of course, once you have a velocity and you have radius, a distance, you can always take r square and divide by v square and you will get some time, which is what I have done. You will get time squared. Okay? Okay. Yeah. There you are. Then you can look at the binding energy of the whole system, gravitational binding energy. So, if you had to, you got the system, if you want to dismember it, take apart all the things and take them away to infinity, how much energy will you have to input? That's the same as the energy which would be released if the whole thing came from infinity and arrived at its current mass and radius. Okay? Again, you're kind of forced to gm squared over r. Maybe you can do a little better. You can cut it into 2 halves. Of course, no one taught you how to calculate the gravitational force between 2 hemispheres. Right? It's not that simple. And of course, the density may not be uniform. It comes out that it's not really gm squared over r, but there's some factor in front, like 3/5, depending on what the model is. Okay, you know the total energy, it happens to be the potential energy which we calculated, but we also know that the kinetic energy is going to be similar. Okay. So, you can ask what's the energy per unit mass. Okay. Now, that has, or I'm calling it energy density, and you will see that in just from laboratory physics, that the pressure is of the order of energy density. Of course, one thing is that pressure is force divided by area, and if you multiply both numerator and denominator by length, you will get energy divided by volume. But quite apart from that, if you look at the formula for pressure in kinetic theory of gases, or if you look up kinetic theory deals with classical gas in which things move around because of temperature, but you might be dealing with a quantum gas in a metal, in which case the movement is because of the uncertainty principle and Pauli principle, right? It could be at absolute zero, but you can't pack all the electrons in the same state, so they pack up to something called the Fermi level, which I think is taught definitely to people even, right? So, whatever it is, you can make an estimate of the pressure. So, just based on arguments like this, people in even the 19th century said they could estimate the temperature because just using the ideal gas law, and it came out to be some 10 million degrees. You can do that calculation yourself. If you will come up with a similar number, you will have to use the gas constant, things like that. That's certainly much more than the temperature at the surface of the sun, but maybe you shouldn't be surprised because you have a high temperature in the center and the energy is flowing outwards down the temperature gradient. And, okay. So, you can also calculate an energy per particle, which is sometimes relevant. And of course, in the case of the sun, you have a certain number of protons, same number of electrons. But it can also be applied in a star cluster, in which case the so-called particles are just individual stars. So, there is something called a globular cluster in which you have maybe 1 lakh stars moving around in a region of about 1 parsec. If the weather were better, you could probably see some of them through a telescope. Okay. But in the case of the matter inside a star, it's important to note that the energy per particle can have two possible origins. Just the temperature if it is in a classical regime, and if it's in a quantum regime, and I will tell you what that is, right? Then it depends on the density. Because I mean, it's easy to see why it depends on the density. If you put the electron in a smaller space, uncertainty principle tells you that the momentum goes up, and therefore the pressure goes up. Okay. Now, interestingly, suppose we knew pressure as a function of density. That means you know m squared over r fourth as a function of m over r cubed. So with little bit of rearrangement, you can definitely get m as a function of r. Okay. Shouldn't be difficult. I'm not going to do it, but as a matter of principle, I can do. So, incidentally, this pressure as a function of density is somewhat unusual in astrophysics. What is more usual is pressure as a function of density, number of particles, but also temperature. Temperature is an independent variable. Okay? But there are cases where the temperature is not that important because for example, if you take something like the planet Jupiter, it's at a fairly low temperature. So most of Jupiter, the hydrogen is compressed, it becomes ionized, and it's a quantum gas. So it's interesting that you are taught about free electrons and Fermi level and all in the context of metals, but it equally applies to most of a planet like Jupiter. Okay. So there is a class of bodies in astronomy which you can call cold bodies. Okay, doesn't mean they are at absolute zero. It simply means that the energy per particle comes from the uncertainty principle, not from the temperature. Okay. Okay. So now I have a kind of diagram. We'll spend some time on it. Oh, we spent quite a bit of time. This is particle density on one axis and temperature or energy density, either of them. Epsilon is energy per particle, which would be Boltzmann's constant into temperature, but otherwise it would be some function of density. Okay. So I've drawn lots of lines on this diagram, and let me see if I can tell you. So I guess one important line is the line which separates quantum behavior. So this one, I've written D on this side of the line and non-degenerate on this side of the line. So by the way, if you look at the sun or something, the density is somewhere in this region, but the temperature is way out, right? Millions of degrees. So it's well on the classical side. But if you take a star which has the same mass as the sun, but is much denser, and there is a set of such stars called white dwarf stars. And, I've also written the names of various astrophysicists, but we won't get into them. They really live. So actually, once you come here, it's not even meaningful to go here, because if you give this much density, this much energy density, I'm calling it log of T, but it could also be log of epsilon, the energy per particle. So this is the degenerate line. Okay. Now, interestingly, there's another question you can ask. All right, let's say you have protons and electrons. Can you neglect the potential energy between them, electrostatic potential, which again seems to depend on density. So as you compress, the separation becomes smaller, so you would think potential energy would dominate. But that's only true if the kinetic energy remains fixed. But if the kinetic energy also increases because you are compressing, right, which is what happens because of the uncertainty principle, then actually it becomes more like an ideal gas. Okay, so that's an interesting thing. So in solid state physics, people worry a lot about whether the electrons are really free or whether the Coulomb interaction is very important. Interestingly, Mott is the Nobel Prize winning condensed matter physicist who investigated this. But a little before that, our own D.S. Kothari wrote a paper on the interior of planets by Jupiter. He called it pressure ionization. So as you compress, the Coulomb force is too weak, electrons get freed, and then it starts behaving like an ideal gas. So that's why I have. So Of course, once you are above this line, you can treat the electrons as free. I mean, this is that line. Let's say you are on the classical side. You can still ask, if you take hydrogen atoms, will they be neutral, or that's N, or will they be ionized? And this is on the classical side, so we are just talking of temperature. And you can see it depends very well. The temperature is somewhere around 10,000 degrees, but it depends very steeply on density. And of course, once this line hits that line, you don't worry anymore, because the electrons are kind of free. Okay, so this is just to give you kind of different states of matter which are relevant inside planets, inside stars. Okay, so I think I've already told you most of these things. There's one more line. So at a given value of particle density and temperature, you can calculate gas pressure. Okay, but just given the temperature alone, you can calculate radiation pressure, because you have a black body law which tells you that at any given temperature, the energy per unit volume is proportional to fourth power of temperature. It doesn't say anything about density. The photon can be created and destroyed, so the density keeps adjusting as you heat it up. So this line was actually drawn by Eddington, and it's a very interesting calculation, because he simply says that if you had some physicists who had never seen a star, and you ask them to predict, could such a star exist, what they would probably do is equate radiation pressure and gas pressure, and they would arrive at a point on this line. Okay, I mean, that's just a nice. Curiously, this line is parallel to this line, but if you take again the conditions see, the sun is not really dominated by radiation pressure, somewhere here. But if you take stars of higher mass, they actually have, interestingly, they have slightly lower density and they end up on this line. They're dominated by radiation pressure. Okay. So that's a little bit of the physics which is happening. Yeah. Okay. So that was N versus T. And I told you, in principle, if someone gives you N versus T, some points on that, you can say something about M versus R, in principle. Now, I'm not going to ask you to actually do the calculation, but I have put down, actually some kindly person has put it down, all right? And the first thing you should notice, this is a very rough diagram, okay? So, if you look at the radius, it's in kilometers for some reason, going all the way from 1 kilometer, which is a bit low, all the way to, 10 to the more than 1 million kilometers, okay? So, really huge scale. So then, with calculations whose basis I have told you, knowing the relationship between pressure and density and temperature if needed, planets look like this. So Earth is about 1 lakh times lighter than the sun, which is why it's sitting at -5. Jupiter is about 1,000 times lighter than the sun, that's why it's sitting at -3. But interestingly, a lot of objects have been discovered here recently, right? Extrasolar planets, and then some objects here which are brown dwarfs. Something very strange happens, and which is Kothari pointed out, that there's a maximum radius, okay? About 70,000 kilometers, is that right? Yeah, somewhere here. Little less than 1 lakh kilometers. And then you add more mass, but the object starts shrinking. And the reason is that, I mean, it comes out if you put the correct equation of state. So basically, for normal matter, P rises very rapidly with rho. And you can see if you try to compress something, it takes a lot of pressure. But at some point when this pressure ionization takes place, which was pioneered by Kothari, you get free electrons and they are easier to compress. So these white dwarf stars actually are the same size as the Earth, okay? But look at the mass, it's much bigger, right? Okay. Now on this line, you can draw R proportional to M. And from what we said earlier, those would be lines of constant escape velocity, okay? So those lines would look like this. So here is this line, which has this nice 45-degree slope, and this is for escape velocity being of the order of the velocity of light. Now, such objects are called black holes. You will hear more about them, so I won't say more about them here. And there are these objects which are very close, neutron stars. Look, the mass is not that different from these white dwarfs. Log is 0, so solar mass. But look at the radius, 10 raised to 1, 10 kilometers or something like that. And of course, all this was theory in the 1930s and all very well determined by observations nowadays. Okay. Wait. Yeah. Now, I thought, having shown you the theoretical diagram, since lots of extrasolar planets have been discovered, and I told you how from transit you can find the radius, and from radial velocity you can find the mass. So, people have actually constructed a diagram with, and it looks, except the axes have got switched, I think, but yeah, no, it's the same order of axes that we saw earlier. So, but the units you have to be a little careful. This is mass of the Earth. Okay, so Earth itself is 10 raised to 0. Radius also is the radius of the Earth. So, Earth is somewhere here, and Jupiter is somewhere here, and these are things which are more massive, but not necessarily bigger in size than Jupiter. I mean, people haven't detected planets beyond this point. So, I just thought I'll show you this observation lemma. Then there are the white dwarfs. Now, the white dwarf theoretical curve is shown here. And as I told you, the radius goes down as the mass goes up, right? And of course, you saw the picture of Chandrasekhar in the morning, and his contribution is to realize that this curve ends at around 1.4 solar masses, purely from the theory. Now, there is some variation in these curves depending on some other details like temperature and so on, which we don't worry about. But so this point is that Chandrasekhar limit, which you saw, okay? And radius is now in units of the radius of the sun, so 100 times less, right? I mean, in this case, 0.01. But the beauty is, thanks to Gaia, that you actually have observational points on this, which you didn't have earlier. And this is by two different methods, which is not that important. And you can see this is really very recent. It is accepted 30th January 2025. So, a lot of these things which are purely theoretical, there aren't that many white dwarfs here, but whatever there are lying close to the curve. Most of them are bunched around 0.6 solar masses, something like that. Okay. Now, I also showed you those neutron stars, and I think you will hear more about them, either from the radio people, the pulsars, maybe from the X-ray people, because the same neutron star can emit X-rays if matter falls onto it. We saw that. I didn't want to show you that curve because there is no single curve, because people don't understand the physics of these interacting neutrons as well as they understand the physics of electrons interacting with protons. Okay? So, I will only make a very general statement that there is something like this Chandrasekhar limit. It's above 2. We don't know exactly where it is. The radii are somewhere between 10 and 12. But people are very keen on doing better observationally and theoretically, because this is a region which has not really been explored in the laboratory. Even the atomic nucleus has a certain density, but in these neutron stars the density is even higher. Everything due to gravity, of course, right? So, you should think of the neutron star as a giant nucleus and the white dwarf star as a giant atom. I mean, very loosely speaking. Okay. So, actually we have up to now been talking of somewhat spherically symmetric objects, but even the Earth is not perfectly spherically symmetric. It rotates and it's slightly flattened, and our solar system is, I mean, the sun is reasonably symmetric, but the rest of the solar system seems to lie in a plane. And in our Milky Way galaxy, of course, there are a whole population of stars which move well away from the plane, but what you see as the Milky Way is a bunch of stars which form a flat disk. So, let us see if we can construct a simple model which will explain that. So, you have a rotating cloud of gas, okay. Of course, stars are supposed to form from gas. Galaxies are again supposed to form from gas. Right? And initially, of course, if you're going to say it's flattened right from the beginning, then you have not explained anything. More likely that the cloud is, roughly the same dimensions and all things, but it's rotating. Then, of course, again, remember the virial theorem. If the cloud is in equilibrium, it will stay that way unless it loses energy. So, in order to form stars or form galaxies, you have to get rid of energy. Okay. In the case of these protostars, it happens by the usual mechanism of radiating from their surface. But even before it actually forms a star, as this cloud shrinks, it has to get rid of energy. However, to a first approximation, the angular momentum may be conserved. So, how can you get rid of energy without getting rid of angular momentum? It's an interesting question you can ask. It's a dynamical question, right? So, again, let me sketch something on the board for you. So, let us say you have some cloud of gas which has some angular momentum, right? And then it shrinks, it gets rid of energy because you are trying to form a solar system or something like that, right? And then, first of all, it's becoming smaller, but one is also saying it becomes flatter, right? And is there a dynamical reason for this? Right? Actually, there is, and I can describe it in more than one way. If you look at the expression of a kinetic energy of a rotating body, right, can be written in terms of angular velocity or in terms of angular momentum. So, if you have some three axes, Lx, Ly, Lz, and you write it in terms of angular momentum, right? So, this will be two. There will be some moment of inertia here, some moment of inertia here, and some moment of inertia here, right? So, now the way I have set things up, right, you can get rid of, let us say the total angular momentum is on the z axis. So, that is definitely there, but you want to shrink, right. So, in other words, of course, this is the kinetic energy which will become more, but the potential energy will also become more negative, that we know. But these terms are 0, right. So, if you make it a more flattened system, you have definitely reduced, you haven't changed the moment of inertia that much around z, but you have definitely reduced the moment of inertia around these two axes, right. But if this angular momentum is not there to start with, you can do it. Or let me explain it in another way. If you write down an expression for Lx, the angular momentum along x, so what would you have? You would have the momentum along z and the coordinate y, and you will have the momentum along y and the coordinate z. Okay. Right? That's what it would look like. And that means, whereas if you look at Lz, that of course has only the things in the xy plane. Okay, so you have dy. So basically, this is telling you that you can get rid of the z component of velocity by some kind of dissipation, right? I mean, you have to get rid of energy, otherwise the object will stay exactly as it is. So when you get, but you can't that easily get rid of the x and y components of velocity. So that's the kind of reason for flattening. What's interesting is that this is a very old idea. For the formation of the solar system, a German philosopher, not even a mathematician, called Immanuel Kant suggested this, that it will shrink and flatten. Okay. So of course, it will, as it shrinks in this dimension, it will start rotating faster because the angular momentum is conserved. So as I said, you cannot get rid of px and py that easily. If you decrease x and y, px and py will go up. So now you have this rapidly rotating disk. maybe parts of the disk become unstable and form planets and so on. But you have to form, yeah. So it's important that I'm dealing with a gas cloud. So gas has different methods of dissipating energy. You have things like viscosity and turbulence and so on, which are all ways in which converts relative motion into heat, right? And then of course, it's not enough to convert to heat because you've not got rid of the energy. It's just become thermal energy. But then it has to radiate and get rid of it from the system. So all star formation mechanisms do involve getting rid of energy in the form of radiation. Okay. So yeah.
Is that how the protoplanetary jets are they a form of heat transfer?
We'll come to that. As I said, we have formed a flattened disk, but we have not formed a star. Now let me tell you a sort of scandalous fact about the solar system. Sun has maybe 99 or more than 99.9% of the mass, okay? But it has only a few percent of the angular momentum. This is something you can work out. Take the mass of Jupiter, velocity of Jupiter, rotation velocity of the Sun. So Sun is not flattened, right? So within this system itself, somehow the object in the center, the densest part, has managed to get rid of angular momentum. Okay? And the question is how? Now, anyway, we have already got a clue that all the angular momentum is sitting in the planets, and the planets form from this disk which is around. So you need a mechanism which will couple angular momentum outwards, and there is such a mechanism. Sorry, I'll have to keep overwriting, but so if you have, just imagine you have two rings. And remember, according to Kepler's law, these will rotate at different angular velocities, right? The outer one will have a smaller angular velocity, the inner one will have a larger angular velocity. Okay? Draw something like that. So you have two rings, and remember these are gas. So there's some kind of friction, viscosity between them. Okay? So then, there is a torque on the inner ring which is trying to go faster, and there's a torque on the outer ring which is trying to make it faster. But the consequence is very interesting, and this is again a peculiarity of gravity, that if you remove angular momentum from this inner ring, it will actually shrink. And if you add angular momentum to this, it will expand. And you take the same formula, but if you now compute omega r squared instead of omega squared r, you will find that this is proportional to the square root of r. Or just velocity into radius will come out to be square root of r. So, on the one hand, you have successive, so remember this is called a Keplerian disk. So, every parcel of gas is rotating with its own private angular velocity, but the net result is that the outer parts get pushed outwards, the inner parts go inwards, the inner parts lose angular momentum. So, enough of them can pile up and create a central object with low angular momentum, right? So, when people worked on star formation, they had two kinds of problems. One is how to get rid of the angular momentum. The other is how to get rid of the magnetic field, right? It turns out that nowadays it's popular to solve both the problems. Someone asked, what is the mechanism coupling these rings? I just said viscosity, but one of the forms of viscosity is actually a magnetic field which connects these different parts. So I'm actually getting into a little more detail than what I wanted to, but after all, it's our own solar system, so we should know something about the current ideas on how such a flattened system could form, okay? And with, curiously, most of the mass in the center, but most of the angular momentum outside. Now, the same mechanism is also responsible for something I mentioned in the morning, except it's more elaborate, where matter falls onto this neutron star. If it has angular momentum, it will form some disk. And anyway, I'll leave it at that. Okay. So, let's continue. So, further energy loss results in accretion, which means some mass going in In fact, most of the mass going in, but most of the angular momentum going out. Right. Okay. So that's a very sketchy account of some dynamical processes involving gravity. Before we get into radiation, I'd also like to point out that on a different scale, similar things are supposed to happen in the formation of galaxies. Right? So the gas it has some angular momentum, and it could form a flattened disk. Now, so we have disk galaxies like our own, but we also have galaxies which don't have any gas disk, and in which the stars seem to move in 3 dimensions, so-called elliptical galaxies. Not fully understood how they form, but one of the theories is that maybe you form disk galaxies to start with, and then if 2 disk galaxies merge, you form an elliptical galaxy. So this theory can be verified experimentally, except it takes a long time, because our galaxy is a disk galaxy, Andromeda is a disk galaxy. Of course, the universe may be expanding, but Andromeda is coming towards us at 100 kilometers per second. So if you wait 5 billion years, these 2 galaxies will interact. Their planes are very different, and people can simulate this on a computer. And you find the stars are thrown in 3 dimensions, the gas collides, maybe forms more stars, and you may well end up with an elliptical galaxy. So that's just an interesting idea. The empirical reason for believing this is that people look at the fraction of elliptical galaxies and disk galaxies, and wherever there are a large number of galaxies, like a cluster, you see more elliptical galaxies. So maybe they were formed by interaction. You know, having successfully explained the disk, the explanation must not be so successful that it says every galaxy should have a disk, right? Okay. Now, I understand. Yeah, sure.
Having read that, what keeps a galaxy together is basically dark matter.
Yes.
Dark matter is in halo form.
Yes. And the reason is dark matter doesn't have any method of getting rid of energy.
Yeah, but galaxy forms a plane. So,
But it's very important to think that the gas forms a plane. Yes, I didn't bring in dark matter, but though I did bring it in the context of clusters. So, dark matter starts out in the state, maybe with a small amount of angular momentum, but is never able to collapse beyond a point and never able to form a disk. So, by the way, there's one more interesting thing. In the early days of computers, people said, okay, let us simulate a disk. So, put n particles and put inverse square forces, and they found disks were not really stable. That the central part of the disk would form into some kind of bar-like structure. On the one hand, that's good because many galaxies have this bar-like structure in stars, but not every galaxy has it. And then people did the simulations with a halo of dark matter, and they found that it stabilizes the disk. So these two interact with each other. So I'm glad you asked. Yeah. Okay, I'm sort of switching gear. Now, clearly, radiation is important. I mean, if you just had gravitating objects, of course, as I told you, even to form them, you have to get rid of energy. And, I'll just make a few remarks, okay? All the observations, I said almost, because otherwise my friends in ICTS and in the India Neutrino Observatory and all will not forgive me, right? But even at a very zero order level, one can ask a simple question. You have an object, you're getting radiation from it. Are you getting it from the volume or are you getting it from the surface? We take it for granted that for most of the objects we see, it comes from the surface. But that's not completely true. If you, next time you turn on your gas, you'll see a blue flame, but you can actually see through it. So astronomers have a bit of jargon for this. Optically thin means that the radiation is coming from the entire volume, which means that in the journey from the inside to the outside, there isn't enough matter to absorb that radiation again. Optically thick means radiation coming from the center, or from inside this object, gets repeatedly absorbed and re-emitted. Now, this subject of what happens when radiation is repeatedly absorbed and re-emitted was actually investigated quite thoroughly, not in astrophysics, but in the laboratory in the 1850 or something like that. Okay? So, you might have heard of black body radiation, and the black body is really a metal, hollow metal thing with a small hole. So, if any part of that thing radiated, it's very unlikely it will come out straight through the hole. It will bounce around several times, getting absorbed and re-emitted, and then come out through the hole. And it was found that this radiation has a very universal shape, which I'm sure Shiv Sethi will tell you about. And the correct formula was found by Planck, which is why his name is attached to the satellite which studied the black body radiation filling the universe. Okay. But the point I would like to make is, I mean, of course, a star is not like this, right? It's not enclosed in a box. But one can still make an argument of the following kind. It has some emission and some absorption. Okay? Now, if the depth to which you can go and you can look inside depends on the absorption. Okay? So, the formula is exponential minus some alpha times L. So, this alpha times L, alpha is some absorption coefficient, determines, and if it's of the order of 1, then you won't get any radiation from behind that. Of course, you will get it, but it will not come out straight to you. So, you are looking at a layer of size alpha and it has some emission property epsilon. So, what comes out is a ratio of epsilon and alpha. Now, there is this fantastic law given by Kirchhoff that different bodies may be different, but the ratio of emission and absorption should be the same. And this Kirchhoff did purely, I mean, if you have seen a picture of him, he's a man with a big beard, very thoughtful looking. He arrived at it just from the black body radiation experiments. But of course, later on, we understand it today, and it's Einstein who contributed this, that absorption and emission are just two reverse processes happening between the same pair of energy levels. So, if absorption is stronger, emission is also going to be stronger. So, that's a little bit that I can tell you. And if you're dealing with an optically thick body, the good news is you can find out its temperature. The bad news is you can't find out anything else because it will have this Planck spectrum. Fortunately, our sun is not a perfect black body, okay? And it's also not at a constant temperature, right? As you go inside, the temperature becomes more. So, people have learned a lot by studying the spectrum of the sun, spectrum of stars, okay? But as I said, this is a little bit which I thought I'll introduce you to, and you can keep it. So, finally, energy sources. Okay. Now, one can talk of energy per unit mass, okay, and just dimensionally, it's the square of a velocity. So, instead of telling you that some particular source of energy has so many ergs per gram, which you will have to figure out what it means, I am going to take the ergs, divide by the grams and take the square root. And that the velocity is something that we can imagine, we can understand. So, what is chemical energy, right? So, how did I get 10 kilometers per second? Take 1 electron volt, which is like the binding energy of molecules, not so much atoms, right? Atoms a little more. So, that's 10 minus 12 in CGS units, which I am sure none of you use. And then you divide it by the mass of a proton, which is 10 minus 24. So, you get 10 to the 12 in the numerator, take the square root, 10 to the 6, that's 10 kilometers, okay? That's all you have to do. So, this gives an idea, and this actually tells you that if you have the chemical energy of a rocket, it's just about enough to lift it to the escape velocity, okay? In fact, they have to use a reaction hydrogen plus oxygen, which releases a lot of energy, cryogenic engines and all that. Now, what about gravitational energy? We had that up in the beginning. We had total energy, and you can divide by the mass. It's essentially energy per unit mass comes out as gm over r, the same as the escape velocity. So, the escape velocity from the sun, it's a few hundred kilometers per second. So, either you can sit and put numbers and calculate it, or you can take a shortcut saying the mass of the sun is some 3 lakh times the mass of the earth. So, v square would be increased by that, but unfortunately the radius is also some 100 times, right. So, finally you find that it's about maybe 60 times the escape velocity from the earth. So, the gravitational energy of the sun definitely is more, 100 kilometers per second, 10 times more than chemical energy. So, that's why Kelvin and Helmholtz said it must be gravitational energy of the contracting sun which powers the sun. But then if you take the luminosity of the sun, the rate at which it's getting rid of energy, you will find that this won't last very long, okay, last maybe 10 million years or something. Of course, being physicists, they said, fine, 10 million years is enough. But immediately, geologists, biologists, and others told them that 10 million years is not enough. You please give us a couple of billion years. Otherwise, we cannot do our job. And then, so now let's look at nuclear energy. Now, chemical energy is measured in electron volts. Nuclear energy is measured in mega electron volts. So, once you've gained a factor of 10 to the 6 in energy, you will gain a factor of 10 to the 3 in velocity. So, we are now talking of 10,000 kilometers per second as nuclear energy. And because with respect to 100, it's 100 times more, right? I mean, the velocity is 100 times more. So, the energy is 10,000 times more. So, instead of Kelvin and others saying that the sun will last a few million years, now it comfortably reaches a couple of billion years. So, nothing to worry. Huh? Now, interestingly, there is one kind of supernova in which I think a white dwarf star undergoes a nuclear reaction and that's enough energy to blow apart the whole star. Okay? So, that's a very interesting illustration of the power of nuclear energy. But that's not, the story doesn't end here, okay? Because there are objects which are putting out enough energy that it cannot be explained even by nuclear energy, okay? So, I mentioned accretion, objects falling out of neutron stars, black hole. Now, the ultimate limit is, you would say, the rest energy, mc squared. So, I told you we are going to measure energy per unit mass as the square of a velocity. You can't go more than the velocity of light, but actually you cannot even reach that unless someone has very kindly provided you with matter and antimatter, and then you can put them together and get the full mc square out. But our universe seems to consist mostly of matter, so you can get out about 10%. So that corresponds to, so I think instead of thinking of different scales of energy, it's good to think of different scales of velocity, which is really equivalent. And when things fall onto black holes and neutron stars, they are able to release almost 10% of the mc squared energy, rest energy, right? So there is an entire subject called high energy astrophysics which deals with such objects. It's also interesting to ask in what form does this come out? It doesn't have to come out in the form of radiation. It can come out in the form of some jet, it can come out as magnetic fields. I mean, so this is a very thriving subject, and the answer is different for every kind of object. Now, this is the thing which I briefly mentioned to you. The supernova explosion, it's sort of interesting that whenever people talk of an explosion, they really talk of an implosion. The star runs out of fuel because it keeps on burning hydrogen to helium, helium to carbon, and every time you have this fusion reaction, some amount of energy is released. But when you come to iron, which is the most stable nucleus, somewhere around iron, you can't get any more energy by combining two iron nuclei. So at that point, the star gives up. Okay? And by the way, by this time, it's already losing a lot of energy, not just with light, but with neutrinos, which will, at that high temperature, it's losing energy. So then it simply loses support and it collapses on some very short time scale. Okay? Now it's interesting that the central part, then you had electrons and protons and so on, and nuclei, but they get squeezed and they become neutrons. And once you form this neutron star, it becomes much harder. The equation of state again becomes very steep, and therefore the outer part is supposed to bounce and then come out. So all this is an accepted mechanism for supernova explosion. If you estimate the amount of energy, so let's take 10 to the 33 grams as the mass of a star. Then add 21. Why am I adding 21 to 33? Because that is c squared in CGS units, right? 3 times 10 to the 10. So 33 plus 21 is 54. Now, that's of course the total rest energy, but let's take 10% of that. So 10 to the 53. So the accountancy which I told you about in the morning, when you see the supernova explosion, you should account for 10 to the 53 Earths. Now the light comes out at 10 to the 49. The exploding matter comes out at 10 to the 51. So as I said, there is a 99% discrepancy, which can only be explained by neutrinos. And since the number came out right in this one case where we have data, The existing models of supernovae are generally accepted, and astrophysicists will not be accused of, let's say, a lot of missing energy. Okay. Okay. So again, a kind of rapid tour of some more physics-oriented topics which are useful. It's completely not exhausted. I mean, there's a lot of physics associated with magnetic fields and radiation, but I'm sure, this is only the first 2 lectures of an 8-week program, and I'm sure you'll all have a good time. I'd be happy to answer questions, not only here. Many people seem to be more comfortable asking questions there, so I can go there. Thanks.